here we go. PFC physics. My attempt to give you the idea of how this stuff works with almost no equations. So here we go. There's another PFC ball. This one's in Tennessee. Another little quote about numerical modeling, right? So what do we've got here with PFC? Particles, distinct element method. What are the particle shapes? Circles, spheres, overlapping spheres, polyhedra. We can do solid materials by bonding these together. In such a system, we typically think of that as grains. We think of that with grains in cement. That's what we're mimicking. We're mimicking grains that remain rigid. They don't change their shape. All the action happens at the cement. That's where the deformation's occurring. With such a system, we have damage in terms of breakage of the bonds. And we're going to find out that some of the more sophisticated contact models that we need to use to better represent rock than some of the original ones actually allow partial breakage of the cement. And of course, many people use discrete elements to do granular materials, right? Now you just have grains alone and no cement, right? And they interact. And what we're going to find out is that the shape of those grains is super important. If you have a big bowl full of marbles, and then if you have a big bowl full of rice, and you look at the flow characteristics, they're going to be very, very different. And they're going to be different because of the shapes. All right. Here's again that rock cutting example where things are breaking and then they're flowing. You know, here's a broken piece, but it's all an assembly. I'll refer to this broken piece, but it's still a coherent assembly as a cluster. You could think of it as, okay. What do we need to do if we want to write a code and we want to call it a discrete element code? So first of all, we have to be able to have these particles that are in there moving around. And the code has to be able to do all this automatically, right? New contacts have to form automatically. Contacts have to be deleted automatically, right? Any code that does that would be a discrete element code. That's the general term, okay? One particular way of making a code that does this is to use an explicit finite difference procedure to solve Newton's law, okay? And that's what we mean by a distinct element code. PFC is a distinct element code. And then the only other two features that are fundamental to this type of a solution, to this type of a behavior, is that it's dynamic. We're taking small steps moving forward in time. That means that we have a concept of the step size, okay? And we're going to find out that the time step size cannot be as big as you want. It has to be small, and it has to be small because we have to be able to properly forward integrate this equation. And we're going to find out that if the time step gets too big, the system blows up, meaning that suddenly your particle positions go to 1e to the minus 53 or e to the 53. So there's this very well-defined limit of what the time step needs to be. We're going to find out that PFC has an empirical scheme to continuously figure out what that time step limit is. It's going to figure out what that limit is and hit it with a safety factor about 0.8, and that's the time step it's going to use. Since we're just talking about this at this point, to get the idea in your head, think of, oh God, we can do that. Think of the big giant bucket of dry sand that we talked about. And if you smash that thing, there's a wave speed of the wave that propagates through it. Okay. Now that would be simulated with a distinct element method. You would see the same thing, right? You hit it on the top layer of grains pushes down. They then come in contact with the next layer of grains where they make them push down. And this is a wave that propagates through the system. This naturally happens in a discrete element model. Well, it's going to turn out that the time step needs to be small enough that when that information propagates from grain to grain to grain, it's it has to not propagate by more than one grain, because the grain on the third layer is not able to sense the effect at the top until the second layer has begun to move. And so a criteria of time step is that information cannot propagate by more than one grain away. And now think about this. Remember, the wave speed is related to the stiffness. The stiffer it is, the faster the wave speed. That means that a system, a discrete element system, the stiffer it gets, the faster information moves in it. So therefore, the stiffer it gets, the smaller the time step needs to be. Okay, and we're going to talk about that a little bit later. You don't need to you don't need to actually worry about that, because it's going to constantly keep changing. And so, for example, if I'm modeling a dry bucket of sand in a triaxial cell and I'm squeezing it, there's going to be an initial time step based on the stiffness of those grains. But then once I start squeezing it, the system gets stiffer, because when I start squeezing it, there's more contacts that form. So I get stiffer. As I get stiffer, my wave speed gets higher, so my time step has to get smaller. So as you do a compression triaxial test in PFC, as you start applying compressive strain, you're going to see that the time step is going to automatically get a little bit smaller and smaller. Okay. The other thing, because it's a dynamic simulation, is that we somehow have to dissipate kinetic energy, right? If I take a collection of sand grains and I dump them into a box, they bounce around for a little while and then they stop moving. So we're going to dissipate kinetic energy as well. And that process numerically, it's called damping, and we'll talk about that. But the simple damping idea is in your car, right? You have springs in your car. When you hit a bump, your car starts bouncing up and down. And so to stop that, they have damping things in there, those shock absorbers. Shock absorbers are acting to damp out the kinetic energy. Okay. We've already talked about this. You're going to see there's a lot of things we've already talked about. Four entities, right? Particles and contacts. Particles come into contact, and we have this thing called a contact, and the contact is where a force and possibly a micromoment act. And remember, that's an equal and opposite force that pushes against the two guys that are in contact. And here's the example: the forces between these discs. These discs have been pressed down into a box. And the only other thing in PFC are walls, which are surfaces, right? And surfaces have a velocity. That's what you're doing. You're defining the shape of the surface, and you're telling it where to move and when to move. This is the algorithm. This once around is one time step. So let's unpack this. Okay. We have a force displacement law, which means there's been a relative motion between these two particles. And then it says constitutive law. What the heck does that mean? It means that given a relative motion, you have to update the force. Okay. So we're going to say, geez, what'd be the simplest possible one? Well, let's go back to the very fundamentalist idea of force displacement relationship, which is Robert Hooke in 1678. And he did some sets of experiments with springs and with other bodies. And what he found was that the force in the spring is proportional to the deformation of the spring. And so then we have this proportionality constant called the stiffness. Relative motion, delta, we hit it with the stiffness. Remember that there's springs in there. So we hit it with the stiffness, we update the force. That's the force displacement law. So that's updating the contact forces. Then we go to each particle, and it has a collection of contacts. So it has a collection of forces pushing against it. And so we say, oh, we sum up that and we get a resultant force. Okay. And now we have to figure out, if we know the resultant force on a particle, how does it affect its motion? So from 1678, we move forward to 1687, and we say, oh, our good friend Isaac Newton, the father of all of mechanics, ended up determining that the force and the acceleration are linearly proportional by means of the mass, right? So if we know the resulting force on the particles, and we know on a particle, and we know its mass, we're going to be able to determine its acceleration, and we're going to unpack that and eventually get a velocity out of the acceleration, change in velocity. So therefore, we can move each particle. And so now we've moved each particle. Oh, now we're back to the force displacement law. What's the relative motion that just occurred? Oh, update the forces. What's the resultant force on a particle? Update the particle positions. And we just keep doing this step by step. All right. We're going to unpack this a little more. So let's talk about that law of motion, F equals ma. The whole goal is to given a particle and knowing its resultant force, how to update its position. So here's my typical particle inside of a packed assembly. The shapes are totally irrelevant. It's just that we have these bodies which are rigid that are pushing against each other at certain points. So let's zoom in on this guy. As we know now, at a contact, there's an equal and opposite force. We'll just draw the free body for that particle. There's the forces impinging on him. Sum those forces up vectorially. Sum those forces up to get a resultant force. That's the F on the particle, force on the particle. We go to Newton's equation, F equals ma. Now, what are we going to do? This is the derivative. Oh, by the way, Newton developed calculus too to be able to solve this problem, right? So change in velocity over change in time. This is the derivative. So this is still a calculus problem. Now we're going to come, oh, now we develop computers. We need to discretize this. We're going to do a finite difference, right? So the change in velocity over change in time, we're going to write that as a discrete equation. This is the velocity at t plus delta t. This is the velocity at time t. So notice we're introducing a concept of a time step now in order to discretize the equation. This is called a finite difference representation of a derivative. Well, at this point, we've got F, which we know. We've got mass, which we know. We've got the previous velocity, which we know. We got the delta t, which we know. Oh, smokes, holy smokes. We got a simple explicit relationship for the new velocity. So we just rearrange this equation. We come up with this. Here's the new velocity. It's equal to the old one plus this. Let's make a couple statements about this. Notice this is the resulting force on the particle. We'll call this the unbalanced force. It's the sum of all these things. Notice if these guys sum to zero, this is zero, which means that the new velocity is the old velocity, right? There has to be some force acting on something to change its velocity. And notice also that it's also related to the mass, for example. If we have a force acting and we have a small mass, we get a much bigger, quicker change in velocity, right? Knowing the velocity now, we do the same game. We take its derivative of position, we make a finite difference expression of that, and we know everything here except for the new position. And so we get the old position plus the velocity times delta t. So there you go. That's the law of motion. That's this guy. How do we update the positions? Because we move things. And then we got a computer science guy running in the background doing a cool algorithm, which I'll talk about later, of how to figure out when two particles are coming into contact. And then we have to look at that relative motion, that force displacement law. So again, same particle. Now I'm showing the contacts that guy has. In the world of PFC, there's particles. We track their positions and velocities and things like that. There's also contacts. We have a list of contacts. Each contact is at a physical location in space. Each contact knows about the two guys that make them up, okay? So let's just zoom in on this contact, for example, between these two guys. What are we going to do? There's a force acting there, remember? This black guy. Now what we're going to do, we're going to form a local coordinate system, okay? It's going to be tangent. It's going to be perpendicular to the local surface tangents here. So it's normal to this surface, okay? And so that's going to give us a normal direction, Fn. We're going to decompose vectorially. We're going to decompose the force into what we're going to call a normal component and a shear component. We can always do that, okay? So this is actually the problem we have to solve. And the goal is, remember, the contact is storing the current force. The concept of a contact model, this step of the process, force displacement law, given relative motion that's occurred, update those. That's what you got to do. So the simplest possible contact model is what we call the linear contact model. This was the contact model proposed by Kundal in his 1979 paper that everyone refers to. And it has 3 parameters. And I'm going to argue throughout this that they're like fundamental parameters. Okay. It has a normal stiffness, it has a shear stiffness, and it has a friction coefficient. You can think of these as a spring in the normal direction and a separate spring in the shear direction. So let's just talk about the simple case, the normal stiffness. Look at this picture. Look at this picture. The ideal way to do this is I should be standing at a blackboard and we do this, but I'm just pay attention here. This is not very hard. What we're going to do here is remember we have relative motion between those two surfaces, relative motion. We're going to decompose that relative motion into a normal increment of motion and a shear increment of motion. So here's the normal increment of motion. We'll talk about that as a gap. Going this direction means the gap is open. Going this direction means the gap is closed. This is the system. This is how that spring system is going to behave. If it's open, there's no force. If you start squeezing it together, the force builds up linearly with the stiffness of Kn. There you go. And this is going to be incrementally done, so I can keep updating. So if I know the incremental amount of squeezing that occurred, I can determine the increment of Fn, and I add that to the current Fn. And now I've done it. I've succeeded. I've updated it. Now talk about shear. This is the fundamental thing here. So this is the magnitude of the shear force, right? Because the shear force, they could be acting in 2 different directions. And in 3D, it's just basically a force that's acting. Think of between 2 spheres. Now what you have is you think of like a disc-shaped surface that has a normal that's elected along the line normal to the shears. And on that disc-shaped surface, you have a shear force. And so let's talk about the magnitude of that shear force. And let's talk about the relative shear motion. And so think of this. If I start making a shear motion, I start going up linearly and that with the stiffness Ks. Okay. So again, just like your skin, it loads up with a shear stiffness. Oh, another thing is in almost all cases for almost all materials, the shear stiffness is less than the normal stiffness. In the models we're going to build, usually it'll be about half of the normal stiffness. But notice then there's a limiting shear force at which you start sliding. And when you're sliding, the shear force stays the same. And that limiting force is the friction coefficient times the current normal force. And so think of this, I'm forcing my hand to go this way. I start sliding, I get to this point, and then I start moving in the other shear direction. And so just like in your skin, right? You slide for a while, now you start going the other way. Well, first it's going to elastically unload, and we're going to use the same slope, and then it would start going like this. And then if you loaded it up, you'd come back. And this is the behavior then of this simple linear contact model. Okay, 3 parameters, Kn, Ks, and friction coefficient. Here's another way of talking about the same system. The 2 discs, there's the force. I'm only showing the force acting on the top one. Break it into a normal and a shear. Normal is related to the normal displacement by Kn. In our system, we were doing a delta Fn and a delta Un. You could do it either way. Here now is the increment of shear force. It's Ks times Us, but then you also have to say, oh, am I slipping or not? So I'm going to have to make sure I'm going to compare the shear force to this limiting shear force. And if I'm bigger than it, I'm going to chop it back down. So what that means is if I'm sitting here, what do? I take an increment and I go up like, where's my mouse? I go up like this and then I check. Are you above the limit? Oh, you are. Choo, push yourself back down to the limit. Okay. Notice also at this point, this is a generalized thing because this normal and shear stiffness might be a function of the properties of the bodies, like a Hertz model. So the Hertz model is still going to work like this. It's still going to have a Kn and a Ks during a time step, but instead of being constant values that never change, it might be some function of the system, right? So this is really, really the fundamental thing. It's not just the fundamental contact model. Any contact model eventually has to turn into this. because we're going to relate normal and shear motion. I didn't mention this yet, but in all the materials that you have, let's do this. Let's mention it now. So in the high level course PowerPoint slide set, I didn't actually go through this. There's materials we have for the course. And it turns out that in in the fall of 2004, I was a professor at University of Toronto. And so, of course, I taught a graduate course called Micromechanical Modeling, right? And you have all those materials. And in particular, what you have is a set of lecture notes. These are like handwritten, hand-printed notes. There's 15 different topics that are addressed, and you have those things. Oh, and I can't open the file. Just a second. Additional material. Where is all this stuff? Talks. That's not where. I'm sorry about this. Grad course materials. Lecture notes. Lecture notes.pdf. There we go. So click. And here's this set of different, these were all different lectures that were given. Talk about rigid body dynamics. Talk about integration of equations of motion, et cetera, et cetera. There's all kinds of stuff in there. So throughout these talks, there's also a whole bunch of journal papers. This is probably not going to work either. That, well, let me fix this. Now is the time to show you. Edit link, grad course materials, papers of interest. I'm looking for papers of interest. Papers PFC model. Papers. I'm sorry, this is annoying. Papers of interest. There they are. So there's a document here, which is kind of like it's my take on the sort of evolution of discrete element modeling, starting with Kundal's paper, talking about the bonded particle modeling, and then all kinds of other stuff. And so these are all then references of this. All of these papers are also in that directory as PDF files. Okay. So throughout this course, we're going to have these little things. Oh, see notes at 4. Oh, God, I'm sorry about this. That should be pointing off to the note set 4, which is just an example of these note sets. Note set 4. And here we talk about Kn, Ks, and friction, springs, all kinds of stuff like that. Okay. So we're not going to talk where you need to get more details. You will get them here. Okay. So here's another attempt to understand this better, to add this idea. So imagine these are cardboard discs. So imagine I overlap the cardboard disc. These are two particles, right? I'm going to make a local coordinate system along, that's the normal direction, center to center. Now there's going to be a contact location in 3D space. So what I'm going to do is I'm going to pull out my pocket knife and I'm going to jam a hole in here. And I'm going to jam that hole along this normal line at the center of the overlap region. Okay. Then I can pull these things apart and notice then what is this? This is the equal and opposite force that's acting at that location on the two discs, which is shown here. When I sum up the total resultant force for this guy about its centroid, notice this is where the force acts. It does not act on the boundary, okay? Because we do this, these systems are still going to make physical sense even when the overlap becomes relatively large compared to the radius, okay? So that's the idea. Every contact has a position in space. In 3D, it's going to be the same thing. Now there's going to be an overlap volume that's we're going to be worrying about, okay? This is just an interesting thing about Hooke, again in 1678. When when you write the most fundamental paper, you can give it these great names. The name of his paper was Of Spring. And what's interesting about this is he did experiments on this. This is a figure from his paper on springs, right? He just put weights in there. He measured the deformation of this thing. But then he went and he did experiments. He realized it's not just this spring, it's all bodies. And he did experiments, metal, wood, stone, baked earth, hair, horns, and that's why he said every body, every springing body. That's like a huge sort of leap, if you will, right? And then, of course, that linear relationship between force and deformation is what we call now Hooke's law, right? So this was the beginning of all that stuff. And it's interesting that Hooke came before Newton a little bit. Newton is 1687 when he published his famous paper. So there you go. Here's another way of understanding that linear model. Okay, now we're going to draw it in terms of rheological components. Okay, again, here's the example, piece one, piece two. Notice I'm calling it pieces now, not particles, because a clump is made up of pebbles. It's the pebbles that are touching each other. Okay, so this is a contact. It's between two local surfaces, really. What I'm trying to designate here is for this linear contact model, it really doesn't have a radius. It's assumed that the diameter of these two surface patches is going to 0. Green is a line that's drawn onto this body, this piece, and red is drawn onto that. Again, it's designating locally the two surfaces because it's only locally the motion that has to be accounted for here, right? So for example, if this guy was fixed on the bottom, if the top guy, we applied a rotation to it, this point on the surface would be moving in a shear fashion relative to this, right? If I spin this, the surface, there's a relative shear motion, okay? The general linear contact model in PFC also has dash pots. And so here is a dash pot. This is the top surface. This is the bottom surface. There's a dash pot between them. And there's also a different dash pot in the shear direction. Let's not worry about the dash pots. For the linear model, here we go. What is this designating? You move this surface and you squeeze, there's your spring Kn. This is indicating that there can be a surface gap that can form. If you pull on it, sorry, it's not going to stretch. It's just going to open a gap. Pretend that this line is welded rigidly to this, and this line is welded rigidly to the bottom. And so now if you move this in a shear fashion, right, here you go. Here's your spring, Ks. And here's this concept of a friction coefficient. This little symbol here is a slider, which means think of it as like two surfaces rubbing against each other. If I push this down, there's a friction coefficient that's going to limit how much I can push in the shear until it just starts sliding. Okay, so there you go. Kn, Ks, friction coefficient. That's my linear model. Again, yet again, showing it. We've already shown this. Here's the normal behavior. Here's the shear behavior. Okay. Here's the system. Again, we've talked about already this idea of a soft contact approach. That's the baseballs. If I really squeeze them, they form this new shape, but we're not allowing deformation inside of the particles. So our system is going to have overlaps, and our overlaps are going to have springs. The fact that I'm calling it a soft contact approach assumes that there must be a hard contact approach, and there is. And a hard contact approach does not allow overlaps to occur between the rigid bodies. And that approach is not suited to assemblies like this. It's more suited to if you have a bunch of particles flying around in space and they're bouncing off each other. That would be a hard contact approach. That's not what we're doing in PFC. Okay. Now we're going to look at a couple of these things. Here we go. Remember, I was promising you we're going to play some pool here. So we're going to look at what happens if we have a collection of discs just sitting here. They're not touching. We're going to have a frictionless surface that they're sitting on, okay? And we're going to have a particle here, and we're going to give it an initial velocity. So that guy's going to just keep moving. There's no force, no resultant force on him. There's no gravity either. No resultant force. He's just going to keep moving, or he's going to come in contact with this. A compressive force is going to develop, and we're going to see that compressive force work its way through the whole system. We're going to see it bounce off the free surface and go back and then eventually get dissipated. All right, so let's run this. PFC 2D demo. File call. There. And again, for the reasons I talked about yesterday, I'm running a super old 2008 version of PFC because it runs nice and slow. So there's my system. There's my initial velocity. I'm going to represent velocity with what we call a plot item, which is allowing us to draw a vector, draw an arrow at the position of the centroid with acting in the direction of the velocity and with a length relative to the velocity. So now I'm just going to cycle. I'm going to take time steps. And we're also going to do these contact force chains where black is compression. Boom. Did you see that compression wave go through there? Let's look at this one more time. Actually, a couple more times. There we go. Boom. Big high compression at first. It pushes against the other guys, and now they're all just happily going at their own velocities, moving however they're going to move until they interact with each other again. Now we're going to run this slowly. And now I have to hit continue. Here we go. Watch. Big high compression. Pushes that guy. Pushes into the guys next to him. They start pushing into the guys next to him. Notice how we had to be able to track this process. Our time step had to be small enough that this compressive force could go from one to the other. And now they're eventually going to move out. I was teaching a course to people at Dow Chemical some years ago, and I showed this thing, and then the next day the guy shows up and he had made a PFC 3D billiard ball game that could do this stuff. Okay, so what I want to stress on this is this idea. If it's an unbonded assembly, it's all just compression. If you think about it, the only way for tension to develop inside of a granular system is for some sort of glue, some sort of cohesion to be there. There's no cohesion here. So we're just going to have compression. So this is an unbonded system, and it pushes apart.